Okay, very good. So we'll start in a minute.
Yeah.
Yeah, let me have my time with me. Okay, so let's start. Hopefully, everybody is making good progress in a lab session. So today we will continue. So yesterday we had an introduction on the inverse problem for NDE. We had an introduction of signal processing NDE, and particularly for uncertainty quantification. So today we will look into automated data analysis with uncertainties. And we will look at data classification and prediction. At the end of this lecture, if time permits, I would like to share an ongoing research project at Michigan State where we work with an industry sponsor. But I prefer that slides or there are videos in it, so I hope that cannot be recorded. If that's not possible, we'll see, because some of the materials has not been published, and maybe I should not share or publish on YouTube. But we can stop recording, and we can go over the results among the students. I think that's perfectly fine. Okay, so that's a plan. Any questions before I start today's lecture?
1 minute. Sir, can you start the recording, sir?
Oh, it's not recorded.
We made you the host, so now the
Okay.
major rights are with you. You
Okay,
may
so
start recording too.
how about this? How about Niraj? Let me make you host, and you
I am the co-host. I am the co-host, but in that case, you'll make me host, so you'll become co-host, I think.
Yeah, I can be co-host. How about that?
Yeah, yeah, that will work. There, that will work.
Okay. So let me. How can I make you host then? Niraj, how should I do it? I'm not a WebEx person.
Just 1 minute. Just 1 minute.
Yeah.
It is in progress. Getting recording is in progress. Yeah, I think it's getting recorded. Yeah, no issues. No issues.
It's being recorded?
Yeah, it's getting recorded. Yeah.
Okay. All right. Okay, so any questions? If no questions, let's continue. All right, so we talk about data processing, and today's lecture, we will start with the first example or module where we look at data analysis, particularly using a term called confidence measure, CM, or confidence metric, to assess the uncertainties in automated classification of NDE data. The sponsor of this research is EPRI, Electric Power Research Institute. Stop me anytime if you have questions, like what we did yesterday, okay? So this background here shows why automated data analysis is important. Well, from the course 1 and yesterday's introduction, I believe I convinced you that for NDE problems that we're dealing a lot of data, and sometimes the data are either big volume, not necessarily big data, and most of the time the data are heterogeneous, and we're dealing multi-modality coming from different physics. With those data, we want to do several things. One is the diagnosis of damage, or to give a assessment of a complex systems or structure. For this particular example, we are focusing on the nuclear power plant problem, especially the steam generator tube inspection. There are different ways of doing that, and we use eddy current method to explain the idea on the uncertainty quantification for ADA, automated data analysis. Well, there are other examples you've seen, for example, rivets in airplane wings, gas transmission and distribution pipelines. So all those data will be acquired using some form of data acquisition system and subject to analysis to achieve what we proposed or what we discussed yesterday for the different objectives for NDE. For example, to identify the presence of defects and further to characterize the defects. So there are two major aspects of it. The first is sensors. Remember, you see the overall solutions approaches schematic that I showed yesterday, that we always start with novel sensors. And we want to have fast in imaging or data acquisition, high resolution, either in spatial resolution or temporal resolution or both. And most of the time, we also want this approach is economic. In other words, that we can perform more or better NDE sensing with limited or constrained resources. The second aspect of it is data analysis. So today we'll focus on that. This is also the focus of this course too. So how we can develop automated data analysis algorithm to process large volumes of data, as I said, not necessarily big data, that's a different concept. And how we can implement NDE signal processing and pattern recognition to detect the defects and also deal with the noisy measurement with high accuracy and consistency in our final results. I highlight the noisy here. And remember, we have a very good discussion at the end of yesterday's lecture, the difference between noise and uncertainties. So I just highlight noisy here. And although we're using the noisy or noise term here, I hope everybody understand that we are actually talking about more generalized noise, which uncertainties is embedded. Okay. What is the typical data analysis flow or framework? Well, we have a raw data. The first step usually is the preconditioning or pre-processing of data. One key step of it is to do the data reduction because we want high efficient data processing with our computational power. Most of the time, our computational power is limited, right? Unless we have unlimited, resources, either in hardware or we can also have unlimited in software level. But anyway, even with that, we always have like an up limit. So it's always good to do data reduction in the first step. Well, there are different ways of doing it. You can try to reduce the data by filtering technique. Just look at information that you are interested in. You can do thresholding or region of interest detection, so you can only focus on the ROI with limited computational power. The next step is feature extraction. Before that, you have to do the feature selection, which is omitted here. So the second step dealing with the data conversion to feature. The third step typically is classification. In any problem, the simplest classification is a binary one. You just want to see it's a defect or non-defect. There's another thing that I did not list here, and I believe this is always true when we're dealing with data analysis. Besides classification, we can also do prediction. Okay, so there are two major problems. One is classification, and you can predefine the different classes you want to classify the data or feature into. While the second major category is prediction. And there are a lot of ways of doing prediction. We'll cover that in later lectures. But to think about prediction, a simple way of doing that is regression problem. Okay, so let's first talk about classification here because this is what we did for this particular APRI project. Let's look at this example here. I have a example ND response signal, which is an eddy current signal here, hundreds of kilohertz excitation, and this is the data coming from the steam generator tube application. But let's forget about the physics at this stage when I give you the overall idea. Just treat those signals highlighted by those red boxes as possible defect response. Well, you do the data reduction by selecting the region of interest. Then you extract the features. For example, here, feature 1 and feature 2 by assuming that we can apply feature selection extraction algorithms. Then you look at the data in the two-dimensional feature space. While the raw data can be high-dimensional, and you want to look at this in the feature space, most of the time it's a lower dimensional space. So there's a dimensionality reduction approach there. What is the classical dimensionality reduction approach? For example, PCA and ICA and so on, right? Okay, so when you're looking at the data in the feature space, for example, we have class 1 and class 2. One can be defect, one can be non-defect. You want to determine a decision boundary to achieve the classification of those two classes. Well, the decision boundary here can be linear, it can be nonlinear, depending on the distribution of the feature of training data. This can be a separate lecture, and if you are interested in this, you definitely can find a lot of materials online when we're dealing with pattern recognition and using machine learning to do pattern recognition. And you'll see there are different ways of determining the decision boundary. Well, we'll cover that in more detail later, but assume we can have that dashed line determined, which is decision boundary, so you can classify those two set of classes. One is in the lower left corner, those blue stars, and one is on the upper right corner. And if you look at this data closely, you can see along the decision boundary, there are both blue stars and red circles on both sides of the decision boundary, which tells you you will have errors. And we can define them into different types of errors. If you've taken statistics class, you will understand that those are typically the type 1 error, false positive, or type 2 error, false negative. Right? So this is an example of a typical automated data analysis framework. Well, we do this most of the time, but what we can offer when we understand the uncertainties and how we can improve this beyond what we did in the textbook, right? Everything here is like the textbook material, everything works fine, but let me challenge everybody this question. I hope you can see my cursor. So I have a test data here. If I have a new test data, I can,
If possible,
yes,
that we can make that cursor to be this with red shade, that is laser pointer sort of thing. That will look a bit better.
let me do that. How about now?
Yeah, perfectly fine.
Very good. So you can have a new data coming in. When this new data coming in, the classical ADA approach or classification is, okay, I will just tell you this is class 1 or class 2. And from this decision boundary, you can probably tell, okay, this is probably class 2. Pay attention to what you are telling me here. Or you tell me, okay, professor, this is definitely class 2. Or you still have a word in front of that, right? You can say definitely or probably. Well, how can I quantify that? Well, what happens if I look at the data here along the decision boundary? You'll see there's a blue star here. There's a red star, a red circle next to it. How should I classify it? Well, I can simply classify this based on where this data is, either in this lower left region or up right region. But is that a good classification? Hopefully you get what I just tried to make you to think when we look at those new data coming in or the data on the boundaries. I want to look at this in a probabilistic fashion, that I want to quantify this and give some kind of measure and how good my classification or decision is. Before that, let's look at what we have done for many decades. And the objective here, I would call it to assess the reliability of ND signal classification. So just try to translate what I just described into a more rigorous mathematical formulation. Well, one way of doing it is the well-known probability detection, POD. Well, what is POD? Well, we have this figure on the left from a literature. It tells me the POD can be easily calculated as the area under a probability density function where you can have a threshold value ATH here and everything right to that and under the distribution density function will be your POD. Of course, you have to try to look at the CDF function and make sure everything is normalized between 0 and 1. So the area under any PDF is always 1, so you can have your probability is always between 0 and 1. Well, let's look at this a little bit further. I want to help you to understand two things. One is when you set up a threshold, if you move this threshold left and right, what will happen? Well, to answer that question, let's look at there are a couple of distributions here. One is the flaw and noise distribution, or I will call this is the actual measured signal distribution. The measured signal will have the flaw signal plus the noise signal. Well, I still call this noise, or before we define the UQ, literature in previous decades, they call this noise term. Well, that's fine. So we can have distribution here have all the information for floor and noise. And on the left, we'll have another distribution, which is only for the noise only. There's no defect or no flaw here. So we can easily treat this as a defect distribution and non-defect distribution. So my first question or takeaway here is, if I move this threshold ATH left and right, what do you get? How that would affect your POD? There's another term called PFA defined here. There's another shadow region for the small tail, the right tail of this noise distribution or no defect distribution. So you can calculate the area under that. So if you move this ATH threshold to the left, your POD will increase, right? Because the area under the floor and noise distribution will increase. The more close to 1, well, at the same time, PFA will also increase because this small tail, its area will also increase when ATH is moved to the left. What does it mean? It means if I move the threshold to the left, that I will have an increased POD with an increased PFA. Okay, so this is the first takeaway here. The second takeaway is we just mentioned two errors, type 1 and type 2, or probability of false alarm, or probability of false positive, and also probability of false negative, or type 2 error. So what is your type 2 error? Well, if you look at this vertical line ATH, and if you look at the area under the defect distribution, left tail, left to the ATH, this area is your type 1 error. So you can also see if I move this ATH to the left, my type 2 error, probably false negative, will decrease. I believe if you've taken the statistics class, when you talk about POD, there are another figure you can another way of representing the performance of this system is the ROC, receiver operation curve. Well, it shows you the relationship between POD and PFA. So let me use annotate. I will not go to whiteboard here because I can draw those on the same figure here. So for a ROC plot, I have my POD versus PFA. Oh, oops, what happened? Let me do this again. Well, let me change a different color then. I have my ROC plot, so I have my POD versus PFA. Sorry about that. Oops. Okay. P F. Okay. P F A. Well, the worst case is the 45 degrees here, which means that you are simply flip a coin, that your POD is always the same as PFA here. But when you have a better operating system, usually you'll have the ROC curve is similar, typically like this. Well, of course, asymptotically approach 1 here. Well, if you have something like this is definitely not good, right? So another way of looking at this performance is using ROC. Then the more the ROC curve like that, or the better performance it is, which means that at the same probably false alarm, you're going to have a better POD, right? Sorry about this. You have a better POD there. Okay, so this is the fundamentals of probability detection. So for POD, you can also plot the probability detection versus different crack size. And for different threshold, you can see how the POD changes. Well, you can easily try what I just explained. By increase the threshold values, you'll have the decreased POD, right? If I increase the ATH here, then your POD is typically smaller. All right, so now, even with POD, there's something which is not being addressed yet, is even with a POD, how I can assess the reliability of that POD calculation. Well, one way of doing that is to give a confidence measure or confidence metric associated with it. Well, I can have some classified results. It can be defect or non-defect. Look at the proposed measure here, the CM, confidence matrix, in this table. Even I can classify that as a defect or non-defect, that I may have different confidence. Well, we can go back to the previous slide. Okay, let me see, where's my cursor? Sorry, there's some, I cannot see my cursor here. Okay. If I go back to the previous slide, I can have two data points. One is on the boundary and one is far away from the boundary. Well, both of them can be classified into non-defect. For example, this one and this one. But you want to know what's the difference between them, right? So we can introduce confidence metrics to tell the difference. When I change this to pointer, I cannot. Let me see. I cannot see my cursor. Okay, interesting. Is it because of my mouse? Yeah.
We can see the annotations.
Yeah, I cannot see my cursor or my laser pointer for my screen, so I'm trying to find that. Okay. I lost my cursor.
So,
hold on. Yeah, it's back. It's back now. Let me change this pointer back.
Yeah, now it's visible. Yeah, yes.
Yeah. Okay. All right. So with higher confidence, percentage, that I can tell, okay, this is a 2 classification with high probability. That if with low, it's a lower probability for choose 2 classification. But the benefits of doing this, that we can make a self-evaluating ADA system possible. So the quantification of reliability with the uncertainties quantified, that for any ADA system, different from the POD ROC measures that I just explained, we can have additional quantification on how good the classification is. It can also flag indications where operator intervention is required, because when we do the simple classification, good or bad, defect or non-defect, it's just like the final decision, right? But we can hardly tell if it is far away from the decision boundary or close to the decision boundary. So by using the confidence matrix, we can decide if we need human expert to take a look at the data again, or operator intervention. And by doing that, it's possible to enable a single pass system with fewer signals selected for manual review by the human experts. Well, I think this is a typo. This is usually called, it should be called two-pass or single-pass data analysis. A confidence metric can aid in failure prevention by adding the self-evaluating or self-evaluation capability. Well, what I mean two-pass or single-pass, when I have the data acquired, by improve the reliability, that I can have primary data analysis and I can do a secondary data analysis. Well, this gives us more confidence to identify the difference in reported results. So you have to compare and make the final call. During that approach, it's always good to evaluate some confidence metrics there. But you are actually having two-pass framework. For a single-pass data analysis, instead of having primary and secondary data analysis, you can have one automated data analysis by incorporating a effective confidence matrix. Then you can decide whether I need to review selected signals or not. Well, you'll see by doing this, this will significantly reduce the workload that we need to review them manually. And most of the time, the ADA system will take care of it by the new CM capability. Well, next, I would like to talk about three factors affecting the reliability in NDE classification, or how we can incorporate uncertainty quantification in the NDE classification problem. The first thing is the distribution of training data. The second is the size of the training data or the number of training samples. The last is the noise in NDE measurements. I still use the noise term here, but this noise can come in from different sources. But when we looking at the data without, caring about the contribution of different uncertainty sources, well, let's just treat it as something will make our final decision more challenging or confounding our final decision making. So we can just treat it as a noise. We can remove it. All right, so let's understand one by one what I mean the distribution of training samples or training data. If we look at the two clusters here, blue and red, there are two scenarios. Scenario number one, of course, this is a more difficult scenario to classify two sets of data comparing to the right one. Why is that? Because you have the left case, the distance between these two classes is much smaller than the distance between these two clusters. Well, how we define the distance? You can first define the mass, the center point or center mass point of those two clusters, and measure the distance between those 2 points. Another thing that you can notice is if you look at the red cluster here, while the left scenario, the red cluster, the data points are more spread out than the right one, which means that intra-cluster distance the left case is much larger than the right case. Well, we define those interclass distance and intraclass distance as D1 and D2, and we can easily tell that my confidence metric, the quantitative measure, is proportional to D1 over D2. In other words, if I have a larger D1 and a smaller D2, that I am more confident in my final classification. And overlapping features in the feature space, as you've seen from left one, will reduce the classification confidence. Well, how we can deal with this problem? We'll talk about to use Bayes or Bayesian posterior probability approach. Well, the second problem is called the number of training data. Well, this is pretty straightforward, right? This is pretty straightforward, that the more data you have, the better decision you're going to make. Well, this is actually very intuitive. And in data analysis, if you look at this mathematically, that you can explain this in one way using the Chebyshev's inequality, where you can define the probability of the estimated mean of samples, how that is different from the true mean of the population, and the probability of that difference greater than epsilon is always less or equal to the variance of the distribution of the data over n epsilon squared, where n is the number of samples. So if I have larger number of samples here, what will happen? The sigma squared over n epsilon squared will be smaller. In other words, the probability of this estimated mean of those sample points are outside epsilon or mu plus minus epsilon will be smaller with large data set, which means that I have a better understanding or a higher confidence to to explain for example, the mean of this sample data points with more data samples. The third thing is noise. There are two examples here. I just adopted two data from our steam generator tube inspection using eddy current. The left and the right, clearly the right is more corrupted by noise. And we use the same ADA approach, while with noisy measurement, you definitely going to have low confidence of determining what's really going on there, good or bad in this case. In other words, higher measurement noise reduces reliability of classification decision, and hence the confidence will decrease for a noisy data set. Well, how we can do that? So we propose a weight by noise PDF approach. Well, those three different mitigation approaches, I believe you can use this for any generalized NDE problem. And I believe those are three factors you can always face. One is you have different distribution of a training data, you have number of training data going to be different, and always facing the noise issue. So the primary goal of a comprehensive CM is to quantify the effects of all sources of uncertainties into a single measure. So let's see how we can do it. So today's lecture, I will do this, as I said, step by step. We're going to have more like a hands-on approach, and stop me if you have any time by understanding the formulation and each step here. Well, let's look at two distribution here. I will try to generalize this first as AI. Well, later on, we'll apply this to NDE problem. So I just don't want to limit yourself, just think, okay, this can only apply for NDE. Well, this is actually based on the Bayes theory that we can use this posterior probability to update when we have new data coming in, and we can make decision based on the posterior probability. And this is a well-known Bayesian updating approach. And I have two distributions here. One is red, one is a blue. And for NDE, you can simply treat the red as non-defect and blue as a defect, right? And you can simply apply a straight line here, vertical straight line, and you can call this X test. Two takeaways here. The first is, if you're looking at this region, if you have your data point following this pink region, this is the low confidence region. Why is that? Well, from this distribution, you can easily tell that I have overlapping of those two distributions, and definitely it will be more challenging to separate whether this test data is coming from the red or blue. If you have a test data at very left or very right, it's an easy problem. Well, the second takeaway here, I'm probably going to say this later, is how we can make our life easier. Let's forget about all this Bayesian posterior probability here. And I want to ask my students here in the class how I can make my ND decision making easier. In other words, I want to have my higher CM region maximized and my low CM region minimized, right? So how can I make it happen? Any thoughts? Let me open the chat so you can type in. Oh, hold on. How can I make that happen? Well, from those distributions, if I can separate those two distributions, red and blue, easily, or they are far away from each other, then of course I'm going to have lower CM region, right? But how can I do it? Well, let's go back to what we discussed yesterday. If I have a better sensing, if I develop better sensor, if I can process my data better, then my distribution of those data for blue and red, they are more concentrated. Let me draw this on my slides. I'm going to use red here. If I can have a distribution like this, well, I still keep the same mean, all right? Because I want to assume that my sensing is even, it's not a perfect sensing, but I always get the tuning estimated, right? It's an unbiased estimation. So I'm not having any system error here. But the only difference here is my distribution variance is smaller. Well, similarly, for the blue one, I can have, this. I lost my cursor again. Okay, here we go. So this is one distribution. Assume they have the same mean, and I can have another distribution. Of course, it's going to be higher, right? Sorry about my bad drawing here. But what does this mean? Those two distributions are more separated from each other. And my low CM region is going to be smaller. Even I choose the same X test or threshold value there, my POD is going to be increased and my error is going to be decreased. Well, let me repeat this again, that there are two ways of doing this. Okay, I can actually have a better way of understand uncertainty here, just like what I'm doing here. I'm going to explain. Well, another way of solving this problem is to have a better sensing and better data analysis. So they are well separated, so I don't have to worry about a low confidence region. Does that make sense? Okay.
Yeah, that makes sense.
Very good. So now let's look at what we have here. Let's assume we have those two distributions, and I have my posterior probability defined as the probability of A class given the test data. So X test is a pattern vector from a class A. Well, this X test can be feature, it can be data directly from the sensor and so on. And I want to define the posterior probability by knowing my feature or my NDE data and what the probability of that associated with a class AI. Well, from the Bayes theory, you know that the posterior probability is nothing but the likelihood probability of X given AI times the prior knowledge or the prior probability of AI over the summation of all terms for AI, while the denominator, you can treat this as a scaling factor or total probability. Well, we define our confidence metric here and normalize it as the absolute value of this posterior probability minus 0.5 and divided by 0.5. So we can normalize this confidence measure to make it between 0 and 1. Well, how I can apply this to any problem? Well, actually, it's easier that I don't have to worry about more classes. We can start with a binary problem. I can only have defect or non-defect class here, red and blue. Actually, I'd rather shift the color here. I'll make changes next time. I like to have, a defect on the right and a non-defect on the left. But anyway, you got my point. So the confidence of X test classification into defect now can be calculated into this posterior probability, which is now becomes the right-hand side of this equation. And you notice that I make a very tricky simplification here, that by assuming all the prior probability for each class is same, that I don't give any bias there, that I said, okay, probability of defect and probability of non-defect are the same. So I cancel this P of AI for numerator and denominator, so my calculation becomes easier. Right? So I have the likelihood probability of X given defect over probability of X test given defect plus probability X test given non-defect, with all probability AI or probability D of probability of non-D the same, so they can be canceled out. Well, if you want to further develop this, by assigning probability of defect or probability of non-defect to be different, then of course the calculation here is going to be different. Well, I just use that to simplify my calculation to better explain what's going on. But in reality, the probability of defect and probability of non-defect should be different, right? That should be different. Well, similarly, I can calculate the posterior probability for non-defect by giving the data X test in this way. So I have, those probability, this likelihood probability inserted and find my posterior probability. You may have a question say, hey, what is probability of X test given D and the probability X test given non-defect? Those are estimated from the training data set. What does this mean? This probably just tells me if I know this is a defect scenario, what's the probability of getting that data? Well, you can get the information from your training data or from your sampling of your NDE measurement data. There are potential source of uncertainties there. Well, due to the time that I'm not going to go into the details of that, but there's more work can be done here. And also, as I mentioned, the prior probability, it should not be 0.5 for everything, right? That can be changed. But anyway, let's go over this approach using the simplified formulation. So the reliability in classification affected due to the distribution of training features is represented by the Bayes posterior probability. So we can look at the training feature distribution, which is given by the probability x given d and the probability x of given non-d, or the likelihood probability here, and embedded that into our CM calculation. So this is effect number one. The second effect is number of training data. We always deal with the dilemma here that how should we balance our resources to get as much data as we can with the limited resources constraint. Well, we have to deal with limited data set as NDE scientist or engineer. One way of doing that is to do bootstrapping, which means that you can select a subset of the data points from a limited sample set, and you estimate those densities from those subsets. You can do that randomly through this bootstrapping approach and calculate the posterior probability from that. And then you repeat that for other subsets when you do this random drawing, what we call bootstrapping, right? And from that bootstrapping, you can have a vector of Bayes posterior probability. As you can see from here, it's more like a histogram, and you can calculate the 95th percentile value as your confidence measure or confidence metric here. This is a simple calculation of how to calculate C.95 here after you do the bootstrapping. The benefits of this is you can understand the behavior of the entire population from only a small sample set. And the effect of number of training data in estimation of class conditional density from the vector of posterior probability instead of one-shot confidence computation. So you instead of you just have the data, you just give a one-shot calculation. Now you can actually get a distribution out of it. Let me show you some examples of the number of training data and how that can affect our confidence matrix calculation. And this is also very intuitive that with increased number of training data point from n equal to 10, 15 to 20, I'm not even significantly increase the number of data points. That you can clearly see the confidence histogram that I calculate from this bootstrapping or this random sampling of a subset of a data set, that I can estimate the distribution better and better. And my confidence, when you look at this confidence measure C.95, where you will draw, let me see the annotation here, you will actually look at the C.95 here, C.95 here, C.95 here, then this number will become more and more close to 1. And we define this as a confidence metric. Say we are more and more confident. So this CM is proportional to the number of data points by this definition. Or in other words, with the increase in number of training data, the variance of confidence histogram decreases, which is reflected in the increase of C.95 metric. And this is a very clever definition. Okay, so now let's look at the third, is if we have noise in the data, what will happen? Well, this is a pretty busy plot, but let me just highlight what you have seen before and what is new here. For the red and blue, you've seen that before. What is that? That is your conditional probability for different classes. Here, defect and non-defect, right? That's coming from the distribution of the training data or the likelihood probability. So you can have that from your data, red and blue. So when you take your own measurement, you can have those two distributions, probably x given A1 and probably x given A2, or you can replace A1 as no D, A2 as D. This is not new. So what is new here is I want to calculate the confidence now with the corrupted data by noise. Without noise, I can calculate the confidence like what I did before. I can have C1 calculated, but with noise, I will have C noise, which is a weighted summation of the noise distribution, which is defined as the P noise. And this noise distribution can be estimated from my real measurement. And I'll show you an example very soon. Well, in this case, we can simply assume this as a multivariate Gaussian distribution. And as I mentioned yesterday, well, this probably is not a very solid assumption here. And in a lot of cases, this is not valid. But let's start with the Gaussian first, because of its nice properties. All right, but I want to point out that, well, okay, there's a question mark here. But anyway, let's start from it. So my calculation becomes easier. I have a green Gaussian distribution here. Well, it can be multivariant, but now I just show in a simple case here. So what my confidence definition here with noise is a weighted summation that from the previous C calculation, I have my Cx here, and I sample it at different data points, so I can have my Ci times Ni at different x values and add them together. Of course, I normalize that by the total probability of noise. So I will get my C noise distribution here. Well, you can see this is one way of incorporating noise to it. This is not the way of incorporating noise, but this is just one way we do it. And also the noise model here is a simplified Gaussian model. Depends on the physics of your NDE measurement, you can have a more realistic assumption there. Okay, so hopefully I give you the basic idea. At the same time, I want to point out the assumption here, and most of the time the assumption is not valid, so you can expand that or relax that assumption to make it more realistic when deal with a real data point. So this demonstrates the effect of noise in the test data into our CM calculation and how this noise weighted confidence metric gonna work. So this is demonstrated using a synthetic data and synthetic noise here, and the noise is modeled as a Gaussian distribution, right? In this case, it's two-dimensional. Well, the noise is modeled and incorporate into the data point, which is a black cross here, and you can see it has a distribution defined by this multivariate Gaussian. If I don't consider this noise in my confidence metric, what you'll get is going to be a vertical constant or straight line here. But with the confidence, with the noise considered in the confidence metric, you clearly see for increased noise variance, sigma n here, then your confidence will decrease. In other words, if I have a measured data point x or the cross point here, if I can tell something about the noise variation, a noise variance sigma n there, then I can give you a better classification results telling you, how should I rate the reliability of this classification. The higher noise, the less confidence or less reliable. Okay, very good. So I would like to stop here and we can take a very quick look, review of what we just discussed. We look at three contributions or three factors affecting the reliability, and we are actually incorporating the uncertainties into our calculation of confidence metric. The first is how we can deal with the distribution of a training samples, and we're going to use the probability distribution function to describe that distribution, and we incorporate that into our posterior probability calculation and model that distribution of training samples using the likelihood probability. The second is for different number of training sample points that we can use bootstrapping to contribute that term into our CM. The last is we can use a noise model. Here I just demonstrate that using a Gaussian model that I can easily show with a large variance of noise signal that I can have a less confidence. This can be easily expanded to other measurement method, not only NDE. And you can cite our paper and apply this into your own measurement and think about how good my classification, how good of my decision based on my data going to be by considering the different levels of uncertainties here. Very good. I think I intentionally slow down to give you the concepts so we can look at the real problems when we're dealing with the real data. Any questions? If no question, I can move on. If you have any question, feel free to type in your chat window.
I'll just ask the online participants. Any questions from the online participants?
Okay.
You can post it in your this chat window also.
Yes, please do that. All right. So the first half of today's morning lecture is on the concepts and the fundamentals. And as I said, think about how you can apply this into your own data. Well, now your data, when when you look at your data, it's not going to be a binary decision anymore. Or it is a binary decision, but you will have your confidence measure or you have your uncertainty associated with it. All right, let's look at examples so you can better understand what I'm teaching here in terms of concepts. Some background about this, the data we're getting here. This is the eddy current inspection of steam generator tubes for nuclear power plant. And from this figure, you can tell where the steam generator tubes are and why this is a critical NDE problem, because its working condition or environment is high moisture, high temperature, high pressure. And for nuclear power plant, that you also have to deal with the radiation, right, which will degrade the materials faster. So ND definitely necessary. So there are different ways of doing it. Here we just adopt the eddy current measurement. This is a project that Michigan State has been working with EPRI for several decades. So we have tons of data, and we help EPRI develop a ADA system with embedded confidence metrics. Well, other background about the defects here, it can happen at different locations. For example, on the tube itself, on the support plate, and one major issue is the tube wall thinning due to the corrosion problem, and sometimes you'll have corrosion-induced cracking, and those are pretty malignant if you don't detect them timely. Then they can reach to the failure of the structure of nuclear power plant facilities, and this will lead to a downtime and a significant loss in dollars. Well, the data here is from the multi-frequency eddy current testing, and you'll see that we've developed different type of eddy current testing, um, approaches, and with different type of probes there. And this is truly multi-modality measurement, so you can get different information from different, even in the even the same eddy current method with different eddy current probes there. So the ADA has been developed into a software tested by the users, and it will give you the automatic data classification into different defect categories. The picture here showing you the EC response signal after calibration, and this is from the imaginary part of the data from the plus point probe at 300 kilohertz. And the region of interest has been identified here, and you can see some representative defect signal here at this particular frequency. Well, let's try to practice what we just learned. How we can actually understand the confidence metrics when we're doing the classification of the signal here. So I have my measured data here, and also you can see the background, also the tube support response here. There's some signal here we call wear signal, and we have automated determination of region of interest here, and we want to differentiate that from the background signal, and also sometimes the defect signal is very similar to the tube support signal you are seeing here. So we cannot simply tell that based on the intensity differences. Okay, the first step here is to extract the noise and background information. Let's just mask the center part, and by assuming everything else is just the noise or background signal. Well, by looking at this data, you can estimate the noise parameters and try to find the probability density function using a multivariate Gaussian. So by estimating the mu and the covariance matrix here, then you can have a description of the noise pattern or your probability of noise. And now this term makes sense, right? This term x minus x test. Well, this is just a notation. We're not just actually doing a simple subtraction here, but the subtraction here means that I am having this, spatial domain masking, or the simple signal processing here, that I'm only consider the noise signal region. right? So I use this Gaussian pattern, and for this particular signal, it works very well. So you can have this multivariate Gaussian to represent the noise pattern. Well, the step 2 is to implement parameters of noise distribution into confidence calculation. And remember, this is actually effect number 3, that you can incorporate or implement the probability of noise into our calculation. And you can get your C, the confidence without noise, and you can get the C noise by given the X test data. So now when I have a new data coming in, that you are going to have a distribution. Instead of have a single data point, now you have a green elliptical distribution here, right? So you can tell that the confidence of X or new data point without incorporating the noise distribution, that the confidence of that is a defect is 0.98 or 98%. But if you incorporate the noise distribution, the confidence decreased to 93%. Which makes sense, because with the noise that you are not quite sure that this is a defect or non-defect, although 93% is still a very good or higher number, right? But you definitely can see the contribution of noise there. So now look at the more results coming from the real data, that you can have low noise, medium noise, and high noise. And you can clearly see that the confidence matrix, or the measure of this uncertainty here, is changing over the different noise level. And this can also easily or being visually verified from the data itself. And here are different data set, top and bottom, and you can clearly see low noise versus high noise. The signals are very different. And this gives us a very good savvy tool that we can incorporate noise contribution and give you a more accurate confidence measure using this developed metrics here. Okay. Now, two more factors that we need to consider is historical data. The second is multimodality sensing information, or multiple sensors. How we can further incorporate them into our reliability analysis of ND classification results. Before we do that, instead of reading those texts here, I would like to ask a few questions you can try to answer, even if you don't want to type in the chat window. First question is, will this help us in our NDE data processing? Here is the classification problem. Yes or no? The answer is obvious. Yes, right? So more historic data available to us, that we can have a better decision making, by assuming the historical data is actually good. Well, the more sensory data information coming from different physics, or here the same physics, different type of probes, it will also help us to achieve a better classification in the data processing. Okay, then the answer is very obvious. Now the question becomes, how can I do it? Well, you're going to treat the historic data set as a new data set. Well, with that new data set, then I can probably using the same Bayesian updating scheme, right? That's what the beauty of Bayesian updating, right? The Bayesian means that I can always update my probability, particularly the posterior probability distribution, by incorporating new information into it. So every time my posterior probability will be updated with new data coming in, then that becomes my prior probability, the second term on the right-hand side of the Bayes theorem equation. So that's the Bayesian updating. So I can treat historic data as a new data set. Okay, good. I kind of figure out how I'm going to do it. So let's try to do it. Well, the second is how I can deal with multiple data set. Well, here comes a decision to make when we do the research here. I can use data fusion approach. Well, I can fuse that at different level. Remember yesterday we discussed that I can fuse the data at the image domain, for example, at pixel level, at feature level, attribute level, and so on. Or I can also do the information fusion there, so I can consider different sensory data together. Well, today in this lecture, I'm going to show you I can adopt the same Bayesian updating approach, that I can incorporate multiple sensory information step by step. So I can treat the second sensor data, the third sensor data as my new data set. So I can update using the Bayesian updating scheme. Let me give a quick summary here. So instead of doing data fusion, I can also using Bayesian updating to incorporate multiple sensory data or multiple information coming from different NDE measurement. Hope that is clear to you before we move to formulation. So if you understand this, then the formulation becomes easy to understand. When I have a historical data set XH, well, it can be magnetic phase or it can be any form, but it's better that you are dealing with the same physical measurement. Well, then you can have your CM evaluation by knowing this XH. Using the same approach, you see the same simplified equation here. Then this term is the Bayes theorem, right? This is the posterior probability calculation. Well, by omitting the prior probability here, normalize that, you get your C0H coming from historic data. Then when you have current testing data coming in, what you are going to do here, as I just mentioned, the posterior here becomes your prior probability. Instead of having 0.5, 0.5, 0.5 everywhere to start with, now you can have a different probability for defect and non-defect. Does this make sense? So I have my prior probability now been updated using the previous posterior probability. And this is Bayesian updating. So by doing that, I can have my C0 current. Well, although I only have two steps here, one historical and one current inspection results. But I can expand this into a more generalized scenario that I can have multiple historic inspection results, right? I can have the historic data, let's say coming from 90s, 70s, 80s, 90s, 2000, and so on. And I can use this Bayesian updating to update my decision making every time when I have new data coming in. And now new data is kind of coming from the historic. And every time I'm going to update my current confidence based on the previous data set. And the previous data set is going to be my prior probability when I calculate the current posterior probability. Okay? Simple, right? Let me show you some results by doing that. So this is the results coming from two data sets. One is coming from the 2005 data set, the other is coming from 2007 data set. So from the 2000 data set itself, your C0H, we have no previous historic, right? Or we call this 2005 a historic data set. We calculate confidence of it. So we have 65% confident that this is a defect. All right, so you can clearly see for the historic inspection data, it's somewhere here, very close to the decision boundary. 65%, it's very close to flipping coin, 0.5 or 50%. But with new data coming in 2007, we have a new data coming in for the same defect. The flaw may have increased in size, right? Over time, if the flaw is changing over time, then the signal will be different. And particularly if it is a flaw, it's increase the size over time, over 2 years, then your signal magnitude and phase will change. Because of your physical model, you understand how this magnitude and phase is going to change when you have an increased size of a flaw. Right? And let me make it clear that the signal magnitude and phase may not be positively correlated. It may decrease when you have an increased number of flaws. Right? It depends on the physics of NDE method. But anyway, here we know the magnitude is going to change and it's going to be increased when you have a larger defect. And also the phase is going to change. We have a physical model to understand that. But anyway, forget about the underlying physics. Assume we know that physical model, and we try to incorporate the new information on top of the 2005 historic data. Then we can calculate, if we don't consider the historic data set, 2005 data set, I have a 0.78 cm confidence. But with 2005 data set, I said, okay, I am 65%, although it's not perfect. It's somewhere here, but I know it's possibly a defect in 2005. Then I can update my prior probability here based on C0H, and I get my CAH here is 88%. Well, this is a very good example and significant results telling me that by having a 2005 historic decision, that my 2007 decision is actually more confident. I increased this from 78% to 88%. All right. Well, the second example or second step here is to incorporate multi-sensory information. Well, similarly, you'll see the calculation is very similar. The only thing different here is now the data is coming from probe number 1. Now the new data is coming from probe number 2. Probably I should not call this new or old because you may get them at the same time. But we adopt the same Bayesian updating approach that you consider probe 1 first, then you combine that with probe number 2. So you have a composite or compounded confidence. We call it CP1 plus P2. Well, this is another way of doing data fusion, right? But this is different from what we did yesterday at the image level or at the information level. Now I'm just consider everything into this Bayesian updating scheme, and I do this in the probabilistic framework. Well, what do you should expect here? That okay, of course, I want to have more sensory data considered, and I have a higher confidence. And well, this example of showing you that I have two eddy current probes here. One is a pancake probe, the second is plus point probe. And I have the feature space are different for two different probes, right? That makes sense, right? Because I'm dealing with two ways of getting the data. And the physics is the same eddy current, but the data actually different for different configuration or different design of a probe. Well, when I have a new data coming in, now the new data also going to be different, but they are the same location of a defect. They appear different under different sensing mechanism, and I can extract the same feature and I look at it in the feature space and I want to determine whether this is a defect or not. So I can count a CM for pancake is 0.87, but plus point is 0.94. But if I combine those together, I will get a very high confidence results, which is 99%. This is another good demonstration that I fuse those two results together and I get a 99% calculation. One thing I want to point out is this is not a simple mean calculation. Either geometric mean or as mean, right? It's not just simple averaging of these two. Simple averaging, you'll get a confidence between 0.87 to 0.894, which is not correct. The more information coming in, you should have higher confidence. And this approach clearly show you that you're going to have a higher confidence. Now it's 99%. All right. Well, we'll have a conflicting inference example here showing you that when I have more data, that I can even have a conflicting inference that is not always going to increase the probability of decide this into a defect. Why is that? And this is a very interesting thing. And I'm gonna explain that why this actually give us more confidence in our decision making. So I have two types of defects. I'm sorry, same type of defect or two types of sensors. And for pancake, this is what I get. For plus point, this is what I get, right? And you can see for pancake, for this particular sensing method, then you are getting the new data at the decision close to the decision boundary. While for the plus point, it's an easy decision. Well, you can easily tell this from your quantitative measure. The CM for pancake is 55%, around 0.5. For plus point is 86%. Easy decision. And if you do what I just taught, that you'll have the pancake plus point is 63%. What does this tell me? That my confidence, my overall CM of classifying this as a defect decreased from for plus point 86% to 63%, because it's classified probably as a non-defect for pancake, or maybe close to the decision boundary. It might be a defect there. Well, this is actually good. Why is that? That I'm not making a decision based on either of them, based on a single method. I'm considering this based on multiple sensory data. And this tells me I need to look into this further. And this confidence measure is a quantitative way telling me what to do. Should I look at this data further, have human intervention? In this case, yes, because I'm having conflicting inference here. So don't expect you are always going to have increased confidence here, because from multiple sensory data, you may have conflicting decision from each of them. Then this will tell you what to do next. Well, this is a summary of the CM evaluation for multiple coins here, from array, from bobbing, and overall. And you can see for different cases here, for overall, in this case, it increased to 95%. In this case, it decreased. Then you need additional review. In this case, it's even further decrease, smaller than both of them. It's not even in between. And this means that you have to further look into this by the human expert. While in case 1 and 4, this gives you a strong confidence boost. Then you don't really need to review by a human expert. Right. So this actually gives you the foundation of a single pass ADA system, and it can make this into more intelligent decision making when you have this CM considered with all the uncertainties calculation incorporated. Okay, so a quick summary of the first module of today's course here is you can quantify the data uncertainties. And from this steam-generated tube inspection data, we implement the uncertainty quantification using the previous definition, and through that example that we can decide how this confidence metric can help us to achieve a single pass ADA system, and where or whether we need a review analyst or human expert involvement. The reliability assessment of signal classification in ADA is achieved, but I pointed out clearly the limitation or the assumptions we had when doing this simple demonstration. And of course, you can think about how you can relax those assumptions and how to further incorporate more realistic consideration into your reliability assessment. Future work. So other factors of uncertainty affecting the NDE reliability should be investigated. For example, the POD characteristics of each NDE sensor, the prior information about anomaly location and geometry that we didn't consider at all. So those information should be considered as well. And if you are interested in this topic, if you want to become a PhD student in my group, I think this is something you probably should think about. This is something that we are continuing to work on. And apart from Bayesian posterior probability, how we can develop further our new confidence metrics. That's something else is very interesting and appealing to me. All right, so that's the first module. There are a few reading materials for you. For example, why the CM necessary in ADA system? For example, question, what is the advantage of CM if instead one can simply compare the results of, for example, sensor number 1 and sensor number 2, and require review by an analyst for conflicting costs. So this is an example that I want you to give more reading and discussion and thoughts. And I just leave this to you. So I will not cover everything here, but I think the answers here is pretty straightforward. I already give you an answer here. Another thing that not on the slides, and you will see this in my last day slides when I talk about Industry 5.0 and NDE 5.0, is the human factor, or human operator involvement. In this case, you only see the human expert or human intervention when we use human as the review analysis to make the decision, when we have the confidence matrix calculated, and if necessary, you're going to have the human involvement here. But how to consider the human factors in automated data analysis system? That's a big research question. And I want to mention this in the class. It's an open-ended question. I don't have a very good answer as a professor in this area. Well, I have some answers, but I want you to think about that, how we can consider human factors into our research here. And you'll see for the Industry 5.0, although we are still, have 10 years into Industry 4.0 research, but Industry 5.0 is how we can bring human back into our industry revolution. And for NDE, how we can consider human factors better in NDE. So this is an open-ended question. I want to always leave this into my lectures, lecturing. Also, lectures supposed to give you the understanding of fundamental concepts, but I always like to challenge students to think about this beyond what we learned in the lectures. Okay, so the second part is the prediction and decision making. This is for the prognosis study. We have about 20 minutes. I will start this and we'll continue. So I believe we're going to have enough time to go over the Carl project. I would like to take probably a 2 minutes break here, so everybody can catch breath a little bit, digest for 2 minutes, and we could continue this in 2 minutes. So we have about 20 minutes to cover this in our morning session, and I'll be happy to take questions.
Any questions from the online participants?
So I hope that the concepts I covered today, this morning, is clear and detailed enough that you can apply this to your own research. And if you want to know more about this work, you can refer to our paper. And just let me know if you want more information or guidance in your own research. I will try my best to help you. Although my capacity is probably limited due to the other ongoing projects here. So, but I do want the students here can think about your own problem and how you apply that into your own research problem. But different problem, you have to make adjustment or maybe modification, accordingly.
Hello.
Yes.
You have made.
I think your voice is has a lot of echoes, so I don't know. Should I mute myself? I mean.
No, it's okay. I will switch from this mic.
Okay.
Yeah, I have a question.
Yes.
This uncertainty, you have done some matrix evaluation. In this, you are evaluated in a tool. How much time it took give the result?
Well, for the data set we have here, it's pretty fast. This takes at a scale of seconds or tens of seconds if you have an efficient, high performance computing, facility. So this is pretty fast because we are not dealing with very computationally expensive calculation here. Well, For the uncertainty calculation, uncertainty quantification approaches what I mentioned or introduced yesterday when we were dealing with, for example, Monte Carlo simulation, MCMC, then that takes definitely more time. But for Bayesian updating, it takes a scale of seconds. Of course, it depends on what kind of computer you're using, right? But this is pretty fast, and I don't think this will the time will be a bottleneck here doing this updating when we have new data coming in and incorporate uncertainties.
Yeah, so it is a real time. When you scan the SD inspection, you will get the signal, and from the signal itself, we will get the result. Where is the defect?
Okay. I smiled because let me say this.
Hello.
Yes.
Now it is audible.
Yes, I got your question. You said this is real time. You asked me if it is real time or not, and I smiled. Well, it is a little bit unfair to answer this question just based on the uncertainty or CM calculation here, because what you just told me, if you want to make this real time, it means that the data collection, then the data processing, and all those processing we gonna deal with in this ADA framework, it has to be real time. Then you can have a real time uncertainties quantification, correct?
Yes.
You know what I mean? So even the uncertainty quantification or the CM calculation here is very fast. It can be real time, but in the real implementation for the overall system, whether it's real time or not, it depends on a lot of things, right?
Okay.
So if everything before that is real time, yeah, sure, why not? But that's not a trivial task.
Yeah. Yeah.
Yes.
Thank you.
Okay.
Any questions from anyone else?
Yeah, one question. You are using which tool? It is like MATLAB, or you have done any other tool?
In this case, MATLAB. Well, eventually, I haven't tried this on Python or C, but I think if you want to start with Python, well, I think that's a good good direction to go.
Yeah. Yeah.
Yeah.
Okay.
Yeah.
Thank you.
Okay. Yeah, very good. You can easily see that all the plots here are from MATLAB, right? So yeah.
Yes.
Okay, so I don't see any questions on the chat too. So
We'll continue. Okay.
yeah.
Okay, so let's continue. So the second part of today's lecture is prognosis. Particularly, we'll cover the particle filtering based prognosis. And the application here is the composite NDE. And you also see we have multi-sensory NDE methods here. And this is a perfect example and a successful story number 2, where I'm going to demonstrate the inverse problems and signal processing. The sponsor is U.S. Department of Defense and ASNT. Well, okay, quick background. We talk about diagnosis. We briefly talk about prognosis. So the diagnosis, we've talked about this many times, and also in course number 1, I'm sure you think this is enough. And we've developed different sensors. We develop different analysis algorithms. We do characterization. For prognosis is we can estimate the, for example, the damage growth over time. We can try to estimate the probability of failure. We can estimate the failure time or time of failure. And we can use that information to achieve maximum serviceability of a component or structure. The motivation of working on composite NDE and why the prognosis of composite NDE data is important. Hold on, I see a question here. Let me address this first. Okay, so we address everything. We don't have no leftover here. So if defect and non-defect data are overlapped, then how will we solve it? First of all, let me try to understand your question better. The defect, non-defect overlap, you are talking about when we're looking at the feature space that you have overlap of those scatter plots. Is that what you are talking about? Or what, I'm trying to understand the overlap here. Yes, okay. All right, so let's look at let's take just one example here. Let me show you one overlap. Maybe we can start from here. So we have a defect and non-defect here. They are overlapped, right? Well, it's overlap here, and you can see we still can apply our approach here, right? There's no problem at all. The only thing that we have to deal with is when we have overlap here, the decision boundary is not going to be simple, and it might be a high order decision boundary. And you can see this problem in pattern recognition, in machine learning, when you try to find a decision boundary and you want to balance the issue of either I want to have a simple decision boundary or I want to avoid the overfitting issue. Overfitting means that the decision boundary, you're going to have a perfect classification results. Then the decision boundary is going to be really complicated. But when you have a new data coming in, it will not work well. And for overlapping region, then there's no simple decision boundary. In a lower dimension, that you can separate those two clusters. But it's possible when you go to a high dimensional space, then you can separate them well, right? That's what I mean, a complex decision boundary. Instead of a line, a 2D line, then you can have a plane or even a more complex plane. You can separate data out, right? So there's two ways of looking into it. One is for overlapped data, you can always have a way of separating them, or you can go to high dimensionality. Well, if you don't want to do that, the approach is still going to work, right? That's just like what we're seeing here. The only thing is that the confidence for those overlap data going to be decreased, which means that for the let's say for the feature space you're dealing with here, that you don't have a high confidence when you have those data point or new data coming into that overlap region. And well, we have to live with it because you chose to work in that overlapped feature space, right? Or you go to a non-overlap feature space with a new way of finding decision boundary. So that's my answer to your question. Is that good?
Is that okay, Neha?
Okay.
Yeah.
Very good. Yeah. If you still have follow-up questions, please keep doing that. So we can discuss it. So that's the purpose. Have in-person teaching, right? Instead of, you read the slides. Okay, so let's continue on the motivation here and why we want to have ND and prognosis of composites. I think I don't need to overemphasize this, and more um, areas and application you see the adoption of composites or those lightweight materials, or not only lightweight, but you have a high strength over weight or high strength to weight ratio. And you see this a lot in, for example, aviation industry, for example, the Boeing 787 Dreamliner. But this also brings challenges. As I said, emerging materials lack of understanding of the material and its failure mechanisms, degradation mechanisms. This brings challenges on certifying and give qualification of those materials, and we need to have new testing methods. So this shows a few examples of the composite failure after fatigue loading cycles. And you can see that a few challenges here. One is, even we make those samples the same. Well, I have to give a double quote here. We think they are the same. They're identical, but they may fail at very different conditions. And here we subject them to fatigue loading cycles, and one fail at 10,000 cycles, the other fail at 3.5 or 3,500 cycles. Well, we saw they are the same. So how we can understand this from the materials failing mechanism, how we can understand this from an NDE point of view. In other words, when we have the data coming in, can we have a better estimation of the time to failure for each individual structure? Well, that's important, right? This is more like a personalized decision making, that by assuming every structure, every system are different. Although, in production stage that we think they are the same. So can we, use prediction to solve that problem? Another example here, you've seen this from yesterday's presentation, that I can have a periodic measurement for here the composite coupon to capture the damage growth over time. And from this information, then I can have a better understanding of the time to failure. And this definitely involves a lot of signal processing and signal inversion here for the decision making, right? Okay, you've seen this before. I will not, explain this again. It tells me that for the diagnosis regime, that we have ND measurement, all those dots here as a measurement data points, and I can use that to better understand the damage level. And this is can be seen as a curve fitting or a regression problem here. So you have your damage level estimated from those measured data point. But for future damage level changes over time, you have to incorporate decision making or prognosis here. And for the prognosis, there are different ways of doing it. One way is purely data driven, the other is model based prognosis. And of course, this will lead to a very natural solution of combining both, which is a hybrid prognosis. And for the prognosis, most of the time you'll deal with the PDF, the probability density function of the parameters there, so you can have a probabilistic estimation of what will happen. Okay. So the challenges in prognosis using a single sensor NDE or single modality NDE is every NDE method has its own limitation. When the system becomes more complex, when the materials become more complex, a single sensor may suffer from noise, just dedicated for that sensing method. You'll suffer from outliers and biases, and incorrect inference from a single diagnosis under uncertainties. For example, the environment damage progression and so on, or damage fading mechanisms, and particularly for composites, which is quite complex in material composition, this will lead to incorrect prediction. Well, one way of doing it, or to solve this, tackle these challenges, hey, let's get more data, and not only more data from one single sensor measurement. How about we get multiple sensory data, and each of them will provide different view of this damage using different physics, and hopefully by combining them, we can have a better understanding of the damage state of in the material structure. So you also see in the previous course module that we have different sensory data, and we can use Bayesian updating to improve the confidence metrics. Well, how we can do this here to improve the prognosis, the prediction of the damage progression. This shows you an example we did in our lab where we tried to introduce the mode 1 fatigue damage here by applying the fatigue loading on those top and bottom part and introduce a delamination into this composite sample. The true length of delamination can be obtained from the optical measurement, which is 7 centimeter, and for B, C, D, you'll see for eddy current inductive measurement for B. For C, this is the microwave high frequency measurement in the near field, and D is from the optical transmission scan at 2.5 milliwatts power level, and it estimates that the I'm sorry, this is a typo. This should be no, I think there's some typo here, but anyway, the caption is not correct. But the distance here from this left to the estimated delamination tip are different. You can see it's 6.2, 8.2, 7.2, comparing to the 7 centimeter length here. Well, every method has its own uncertainties, but how we can combine all the information to get a better estimation of the two lengths of the delamination. Okay, so we start with a similar approach, right? So I group all those concepts together for today's lecture, so we are going to see one method again, and you see how this apply to different problems. So let's start with the Bayesian updating, but this is not the only method, as I just pointed out before. But let's see how we can use Bayesian updating to solve this prediction problem. Well, before the break, let me just give you this, then I'll take a break. We can continue in 2 hours. That I am trying to again estimate the posterior density or posterior probability, F or P of theta given X, where the X is the NDE data, while the theta is the parameters of the indication for damage, right? So what I'm trying to estimate is the probability of given NDE measurement, what that data will infer the damage level. Of course, you'll have some prior density or prior probability of theta, and that's, as I said, is a parameter associated with the damage growth model or some indication for the damage. Well, Bayes' theorem tell me that the probability is going to be, posterior probability is going to be the multiplication of a likelihood probability times a prior probability, while the likelihood probability here, f of x given theta, is a conditional density function. By knowing the damage growth model and what's the probability of get that observation data from NDE. And this can be obtained from our NDE measurement. So I'll stop here and we'll continue to explain this slide and how we can use Bayesian updating for prediction. And we'll define the prediction and the prediction error for our NDE prognosis problem here. So I'll stop here and we'll meet again in 2 hours and your local time 2:30. Any questions before I go?
Okay, I'll just cross check if there's any questions from the audience. Any questions? I don't think, I'll just check the chats too. No, I don't think there's any.
Okay.
Neha's question was already answered. Yeah.
Very good. So thanks everyone.
We'll-
I'll see you guys in 2 hours.
Okay. So we'll take a break of 2 hours and then we'll rejoin at 2:30.
Okay, very good.
Standard time. Yeah. And so this will stop the recording and the meeting will continue like this and will rejoin itself. So I'm not closing this meeting.
Okay, so should I stop recording?
No, it's okay. I'll ask the technical person to just take care of it, or you can make me the host. And
okay, let me make you. How can I make you the host?
just go to my name and just right click it. Then it comes change role.
Oh, I see. I'll make you host.
Yeah. Now I'm the host. Okay. So now I'll just take the responsibility and I'll do it.
Okay, very good.
Okay.
See you in 2 hours.
Yeah. Thank you. Thank you.
Yeah. Bye bye.